All right, let's talk 3D printing. You've probably been using it for prototypes, right? Making cool models, checking fits. But what happens when you're ready to flip the switch and go from prototype to production? Yeah, using it to make real, functional parts that are going out into the world. This is where the game totally changes, and picking the right tech is everything.
So, this is the big question, isn't it? How do you actually make that jump? You're not just making a one-off model that needs to look good on a desk anymore. We're talking about hundreds, maybe thousands of parts that have to work perfectly every single time. How do you scale that?
Because, the whole game has changed. The requirements are totally different. Your design brief isn't about just looking pretty. Now it's about being durable enough to survive in the real world. It's about being repeatable, so part number 1 is identical to part number 1,000. And sometimes it's even about being certifiable for your industry. This isn't a hobbyist choice anymore, it's a serious engineering decision with real consequences.
So, to make that big decision, we've got to wade through the alphabet soup of 3D printing. We're going to zero in on the 4 heavy hitters, the main contenders when you're talking about production-grade parts. First up, we've got SLS, which stands for a selective laser sintering. So picture this, you have a bed of superfine nylon powder, and a powerful laser is literally drawing the shape of your part, fusing that powder together layer by painstaking layer. Now, here's the magic trick with SLS. All that unfused powder around the part acts as its own support. That means no need to design or snap off extra support structures later. It's a huge deal for design freedom. Next, let's talk about MJF, or multi-jet fusion. It's kind of like SLS's cousin. It also uses a bed of nylon powder. But instead of a laser, it has this inkjet-style head that zips back and forth, spraying a special fusing agent exactly where the part needs to be solid. MJF is famous for 2 things, being really fast and producing parts that are isotropic. That's a fancy word, but all it means is that the parts are just as strong in every direction. You don't get that weak point between the layers, which is a huge advantage. Then you've got FDM. This is probably the one you've seen before, right? It's that classic process of melting a plastic filament and drawing with it layer by layer. It's super cost-effective, and on the industrial side, you can print with some seriously amazing high-temperature materials like Ultem. But, and this is a big but, it has a built-in weakness. We call it anisotropy. Basically, the parts are always weaker between the layers than they are along them. It's like a log of wood, easy to split along the grain.
And our final contender is SLA, stereolithography. This one's completely different. It starts with a vat of liquid resin, like a special light-sensitive goo. Then a light source, usually a laser, draws on the surface, curing that liquid into a solid layer. SLA is the absolute champion when it comes to incredible detail and buttery smooth surfaces. But its strength and durability, well, that all comes down to which specific resin you're using.
Okay, so here it is, the big showdown on paper. We've got all the specs laid out in a table, and you can see the trade-offs right away, can't you? SLS and MJF are winning on durability, SLA is the king of surface finish, and FDM is the budget-friendly option. But here's the thing, specs on a chart are just numbers. What does this really mean when the rubber meets the road, when you're trying to make a part that actually has to work?
Well, that's exactly where we're going next. Let's throw these technologies into some real-world scenarios and see how they actually perform.
First up, scenario number 1. Imagine you're making a batch of housings for some new electronic device. You need thin walls, you've got these little clips and snap fits, and they need to be open and closed over and over again without snapping off. Durability here is everything. Okay, so for things like living hinges or those critical snap fits that have to flex and bend without breaking, the powder bed nylons you get from SLS or MJF are they're the clear winner. The toughness of the material combined with that design freedom, remember, no supports, is a killer combo. And because the parts are strong in all directions, those tiny, delicate features aren't going to just shear off. And this isn't just theory. Check this out. There was a pilot program for a new power drill housing. The company switched from a machined prototype to using SLS with a glass-filled nylon. And the result? They slashed the crack rate during failure testing by a whopping 78%. I mean, come on, that's not just an improvement, that's a total game changer for reliability. All right, let's shift gears. Scenario 2, we're headed into the demanding world of automotive. Think about parts that have to live under the hood of a car, brackets, air ducts, that kind of thing. They're getting blasted with constant heat, non-stop vibration, and they're exposed to all sorts of nasty chemicals like oil and coolant. Now, this is where the decision gets really interesting. For most of these parts, the nylons from SLS and MJF are fantastic. They've got great chemical resistance, really balanced strength. But if that part is going to live right next to the engine block where it's facing continuous temperatures over, say, 120 degrees Celsius, well, then you might have to look at industrial FDM with a super high-temp material like ULTEM. It might be your only choice, even if you have to accept that weakness between the layers.
Okay, last scenario. We're talking consumer goods. Think about the sleek casing for a high-end Bluetooth speaker, or maybe the mount for your fancy bike computer. Here, aesthetics are a huge deal. The look and feel have to scream premium. But at the same time, it has to survive daily life, getting dropped, getting flexed, being handled all the time. It has to be beautiful, but it also has to be tough.
And here the trade-off is just crystal clear. If your number one absolute priority is cosmetic perfection, you need a surface that's ready for a high-gloss paint job right off the printer, then SLA is your champion. No question. But if your product has to survive being tossed in a gym bag and relies on snap fits that can't fail, then the superior toughness you get from SLS or MJF nylon is going to give you a much, much better balance between looking good and actually lasting. Okay, so we've looked at the specs, we've walked through some real-world examples. How do you actually pull the trigger and make the call for your project? Well, it all boils down to a really simple but super powerful way of thinking about it. Here's the secret. The very first thing you have to do is pick your hero criterion. What is the one single most important thing that your part absolutely must do to be successful? Is it insane mechanical toughness? Is it flawless cosmetic perfection? Or is it surviving crazy high temperatures? You have to start there. Define your hero. And once you've identified your hero, the choice suddenly gets a whole lot easier. Look, if your hero is durable, repeatable nylon parts with tricky internal channels, you're going with SLS or MJF. If your hero is all about that cosmetic precision and holding tight tolerances on a part that isn't going to take a beating, you're choosing SLA. And if your main driver is just hitting the lowest possible cost, or you have that very specific need for high-temp polymers, then industrial FDM is your answer.
So you've made your choice. You know your hero. But wait, before you go and order 1,000 parts, we need to talk for just a second about the practical side of things. And that means understanding the true cost.
So here's a simple formula for your cost per part. But listen, the numbers I can really sneak up on you aren't always the obvious ones. For SLS and MJF, how tightly you can pack or nest your parts in the build volume has a massive impact on your cost. For FDM and SLA, the amount of hands-on labor you need for removing supports and finishing the surface can easily cost you more than the raw material itself. You gotta look at the whole picture.
So at the end of the day, picking the right process isn't really about memorizing a spec sheet. It's about knowing your part, identifying that one hero criterion, and letting that be your guide. All the theory is great, but the real learning, that starts right now with your own parts. Which brings me to the final and most important question. What's the very first part you're going to trial to start building your own dataset?